Hi, I'm Ben-Yaakov. This presentation is entitled Deciphering Manufacturers' Ceramic Capacitors Data. I've taken an example here. This is just an example, no endorsement implied, of a Murata ceramic capacitor. This is a 2.5 volt capacitor, 10 microfarad, and the material is X5R. This is just for demonstration. Among the information that the manufacturer is supplying are these two graphs. One is entitled DC bias characteristic and the other AC voltage characteristic. Now this DC bias characteristic is capacitance as a function of voltage, and the way this thing is measured is by submitting the capacitor to a DC bias, which is changing here up to 2.5 volt because it's a 2.5 volt capacitor, and injecting 0.5 volt RMS voltage. This is 0.5 volt, and measuring the current, and thereby you can calculate the capacitance, and this is now shown here on this graph. This is, by the way, done for 1 kilohertz signal. We call this capacitance with local or small signal capacitance, C sub D, because it is a small signal, relatively small signal, superimposed on the DC. On the right, we have another graph which is also labeled capacitance. This time we have on the horizontal axis AC voltage from 0 to 2 volts. And this is a different measurement. There is no bias here. There's just an AC source. And this AC source now is changing, not like here, which is constant, supposed to be a small signal. Here it's changing. At the beginning, it's a small signal, then it's going up and up and up. And say this point here means that the signal was 2 volt RMS fed to the capacitor. The current is measured. And from these two values of the voltage and current, of course, you can calculate the capacitance, which is shown here. Now, as we see here, the small signal capacitance is dropping, and it's dropping quite a bit, from 10 microfarad to 4.5 at the maximum voltage. Now here, however, we see something very, very strange. It starts with 8 volts, it's going up, and then it's going down. Looking at this graph, and knowing that you have a drop in the capacitance, you'd expect this graph also to drop, and it doesn't. It's just changing in a different way. So the purpose of this presentation is to explain why is this and what's the reason that we see this information, and as it turns out, to clear out some of the information that is supplied here, which some of it is not very accurate and therefore needs some explanation. Let me start off with the very basic information about a variable or a voltage-dependent capacitor like a ferroelectric ceramic capacitor. And this basic information in this Q is a function of V curve, charge as a function of voltage. In a linear capacitor, this will be a straight line. In a nonlinear capacitor, like a ceramic capacitor, a ferroelectric capacitor, it's going to be a nonlinear curve. This is the basic information. All other data are actually derived from this. So here we have it. We can now, on base of this Q as a function of V curve, define 3 different capacitances. The first one I call total capacitance. Let's take this point as an example. This will be the ratio between the charge here and the voltage here, total charge and total voltage. This line represents this capacitance, actually the slope of this line, because the capacitance is Q over V, so the slope here is this total capacitance. And then we have a local capacitance, or a small signal capacitance, which is shown here, for example. It is a function of a voltage also. That is, for any other voltage, it will be different, as is the total capacitance. But in the case of the local capacitance, we are talking about the local slope here. That is, the QdV, the slope here. And this should be measured, of course, with a small signal, as small as possible, to really get the slope. Because if it is not a small signal, you are not getting the actual slope, you'll get something else, which I'll talk about in a minute. So this is the small capacitance definition. Then we have what I call the large signal capacitance, C sub AC, which is a function not only on the voltage and amplitude. Now here is an example. Around this point, I'm injecting an AC signal around this point, and I'm measuring the slope of this signal. Now, as you'll see, this is not the actual slope at this point. It's just an average curve here between these 2 points. And to be precise, I have to take delta Q over delta V. I'll talk about it a little bit later in one of the later slides. So we have 3 capacitances. We have the total, this is here. We have the local, this is here, this slope here, the derivative. And then we have the large signal, like here, could be any point and could be also here. Now, what we are getting from the manufacturer is the small signal. This is here, the derivative capacitance. However, it is measured with 0.5 volt. So this is not really very small signal. In fact, it is a little bit like the large signal, because 0.5 volt in this case will be like from here to here, and therefore it's not actually the slope at this point. So this is not, strictly speaking, the small signal capacitance, but that's what we get. It's a 0.5 volt signal. And then we are getting the large signal, which I've shown here, but in this case it's around 0. So this is an AC signal around 0. And what we are getting is the slope of this signal with different, when the amplitudes are changing. Obviously, if the amplitude is very large, you'll go from here to here. So it'll be a different slope. And that's what we see here. However, as I've said, there is something strange going on in that we have a small value here, and then it comes to a peak, and then it drops off, and we'll explain this in a while. The first step that we need to take is to reconstruct this very basic curve, Q as a function of V, this curve here. As it turns out, you can reconstruct it, you can build it from the large signal capacitor. Now here is how we are going to do it. Let's take this point as an example on the Q as a function of V curve. Now we have here the charge and the voltage, and this line now represents the AC excitation around 0, because this curve, the AC voltage characteristic, is given around 0 DC. So we have a signal which goes both ways. I'm not showing the negative side, just the positive side. So this point will represent some excitation, some voltage which is imposed on the capacitor. And this is the Q and this is the V. Now, what we are measuring in the large signal is Q over V for this amplitude. And therefore, this will be like this point here. So this point, this capacitance, represents this ratio of Q over V. So this is the definition of this capacitance for this point. So what we are going to do now, we're going to do the reverse and look at this point, find the capacitance, and from this capacitance, because if we have this capacitance, if we multiply it by V, we get Q. So if we get this capacitance for this voltage, multiply the two, we are going to get a Q. So we can reconstruct now this point. And then we go to another point, and again find the capacitance, the large signal capacitance, the voltage, and reconstruct the other point. And by that we can reconstruct this Q curve. The first step will be to digitize this curve in order to be able to handle the numbers, and I've been doing it with Excel. So what I did here, I just looked at the curve and picked up a few points, not too many, and reconstructed this curve. So what we see here is actually these values I got from here, and this is now replotted by Excel. And this is the reconstructed curve of the large signal capacitor. There's nothing special about it. I've just copied it and got the numbers. And now, in order to see how well did I do, I'm going to put this plot over this plot. And here it is. So I can see that at the point that I've picked, it's okay. And since they are not that close and that there are that many points, of course, between the points I got straight lines, which is okay for the demonstration I'm going to present here in this video. So this is just the reconstruction of this curve. The next step will be this curve. This is now this reconstructed curve. From here, looking at the capacitance and the voltage, I'm getting the Q's, and I've just plotted the Q now as calculated from this capacitance and voltage, capacitance and voltage. So we got here the reconstructed Q as a function of V curve, which is, as I've said, the very basic information. Next, I can take this curve and get from it the small signal capacitance, because small signal capacitance is the slope of this curve. Since I have now Q, I can look at the slopes and reconstruct CD. That is the small signal capacitance defined as the dq over dV of this curve. And this is what I got. Now, this information has been given by the manufacturer. So I've just reconstructed it. And this is what I got. And this is the information that the manufacturer has provided us. Well, let's see how well did I do, or how well do these two match. So I'm going again to put this one on top of this one. And here what I got. Well, since there are not too many points that I've picked, it's a coarse curve here. And in general, it's pretty close. But there is one big difference, very big difference, and this is this hump here, which we sort of barely see here something, but it's not pronounced as this one. There's a hump here, and then it goes down. So the question is, why do we have this hump? Is it real? Is it just an artifact? Well, it turns out it's real. And let's see what's the reason for it. If we look at this curve, if you look carefully, you see that the slope here is different from the slope here. In fact, this one is a lower slope, that is a smaller capacitance, and this one is a higher capacitance. That is, the slope here corresponds to this point, the slope here corresponds to this point. And then it becomes a smaller capacitance because these slopes are lower. Let me explain it in sort of a blown out circuit, which is sort of emphasizing the effect that I'm talking about. It turns out the Q as a function of V curve looks something like this. This is exaggerated just to make the point. It starts off slowly, and then it goes up, and then it sort of saturates. So the slope here is low. This is a small capacitance. This is a higher capacitance, and this is a smaller capacitance. And here it is. Here is this capacitance here, this capacitance here, and this capacitance here. And these slopes correspond, of course, to the C sub D. And so what we see here is small, and then it becomes larger, and then it becomes smaller. And that's actually what we have here. Now, why is this? Why is this behavior? Well, the intuitive explanation is that the ferroelectric domains, the dielectric domains, are sort of lazy, and it needs some voltage to get them going, to move them, sort of overcome the friction, you might say, and then you start to get the effect of capacitance. So there is an area in which the capacitance or the current is rather small. and only then you can start it. And then there is a saturation effect in which all these domains are ordered already, and another movement requires quite a bit of voltage. So there is an explanation to this, and this is sort of what we see a little bit here. And just to emphasize it, I've just put some lines here. This is the first line, this is the second line, and this is the third line. So this one here, the blue one, corresponds to this value, this one corresponds to this value, and this one corresponds to this value. So this is real. This is something real that we have gotten by replotting or reconstructing the Q or as a function of V curve. It is found in ferroelectric material when you measure them in fine detail, that is, with a small signal. Now, the curve that we got was measured with 0.5 volt RMS. That's quite a bit. If you measure this small signal with 0.5 volt RMS, it will sort of smear this thing off, and you'll get something of the average value, which loses all the detail. So this curve should have been measured with a much smaller signal to get the fine detail. So here we are missing the details because it is a too large signal. And here we have another problem. And the problem is that this curve is measured around 0 DC. Now, this is not a usual operating point. Like in a converter, in a PWM converter, you have a certain bias, and then you have a signal superimposed on it at a given DC value. So this information is really not very useful to work with, and I'll talk about it in a second. So based on what we have seen, we can make some observations now. The ceramic capacitor, the ferroelectric ceramic capacitor, is nonlinear. So with large sinusoidal voltage excitation, the current will be distorted. So conventional LC meters readings may be in error, because if you measure the capacitance with the large signal as IRMS over VRMS with a constant here, then this IRMS is wrong because it is distorted. It has many harmonics to it, and it really doesn't mean that much for a nonlinear element like the capacitor. So what is really needed to be measured is delta Q over delta V for the large signal. So this is important to understand. The other point is that the large signal capacitance is given by the manufacturer for 0 DC bias, that is around this point. And what is done is that around this point, the amplitude is becoming larger and larger, and this is how you got this curve. But that's not where you'd like to work, because seldom you'll use these capacitors with a signal around 0. This may be only in, say, resonant converters, but certainly not in PWM converters or DC coupling cases. So this curve is really not very useful. What you'd like to have is the large signal as a function of voltage, that is for various or different DC voltage. For example, here, we'd like to see this large signal, say at 1.75 volt, which is like here, around this value. Now, obviously, the large signal capacitance at this point is different from the large signal capacitance at this point. This one is pretty high, and this is much lower capacitance. So what is really needed is a family of curves for different bias voltage, which is not given. However, luckily enough, if you reconstruct this curve, this Q as a function of V curve, you can very easily build up your own family of curves and see what will be the capacitance at a given bias voltage. I'm talking about capacitance now for large signal. We have resolved the question about this hump and we have seen that the reason for the hump is the changing slopes in this Q as a function of V curve. We can now explain also the reason for this peak in this large signal capacitance. And again, the reason is the behavior of the Q as a function of V curve. This one is the one reconstructed. This is just for demonstration. I'm talking now about the large signal capacitance. Well, the reason is again that as the amplitude of this measurement is becoming larger and larger, and remember this is done around zero. I'm showing here only half of the voltage. It's like plus minus around zero, or with zero bias. This is this measurement. As we increase the amplitude, the horizontal is the amplitude of the excitation. So as we increase the amplitude, we can see that the slope is becoming larger and larger. Here it is, becoming larger and larger. We see to some extent in this reconstructed curve, which is very coarse because we have here only a few points, but still you can see that at the very beginning you get a lower slope and then it becomes a little bit larger. So this will be this portion here. And then as the amplitude is becoming larger and larger, we hit this region which is toward saturation, and then the slope is becoming smaller. So here it is. We got to sort of a maximum here, and then it starts to go down, and here we see it. So as we can see, the explanation of this curve is the fact that we have a changing slopes, and as we change the amplitude, we are moving along this line. Now, obviously, if the capacitance, this large signal capacitance, will be measured around, say, this point, it'll be a different story, and this curve will look entirely different. So this shape is unique to the case of zero bias. This brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it interesting and that it will be useful to you in the future. Thank you.